By 2025, technology won't just change how we live. It could decide if we survive. From life-saving breakthroughs to world-altering risks, these 14 innovations will shape humanity's future in ways we've never seen before. Artificial photosynthesis. Artificial photosynthesis replicates nature's method of converting sunlight, water, and CO2 into energy, but with far greater efficiency. Experimental systems can produce liquid fuels, plastics, and industrial chemicals, with some pilot plants already transforming captured CO2 into carbon-neutral jet fuel. Unlike natural processes, these devices work year-round and can scale for industrial use. Scientists believe this technology could decarbonize sectors like aviation, shipping, and manufacturing while helping reduce atmospheric CO2 levels. If adopted globally, it may replace fossil fuels in key industries. Currently, artificial photosynthesis is transitioning from lab research to early commercial trials in several countries, showing strong, real-world potential. Sustainable aviation fuel from air and waste. Sustainable aviation fuel, SAF, made from captured CO2 and renewable energy, is progressing from pilot projects to industrial production. Using processes like Fischer-Tropsch synthesis, atmospheric CO2 or waste gases are combined with green hydrogen to create liquid hydrocarbons fully compatible with current aircraft engines. By 2025, facilities in Europe and North America began producing small but commercially viable quantities, with airlines such as United and Lufthansa completing successful test flights. If scaled, SAF could greatly cut aviation's carbon footprint while recycling atmospheric carbon. Challenges remain in cost, production capacity, and renewable energy supply. But progress toward large-scale adoption is accelerating. Implantable brain-computer interfaces. Implantable brain-computer interfaces, BCIs, create a direct two-way link between the brain and computers. Companies like Neuralink and Synchron are developing implants that enable paralyzed individuals to control devices purely through thought. These implants record neural signals and can stimulate brain areas to restore lost functions. Potential uses extend to memory enhancement and even direct brain-to-brain communication. In 2025, human trials grew to include more patients, showing consistent success in tasks like cursor movement and text generation. While challenges such as surgical risks, data security, and long-term stability remain, progress continues toward deeper and more advanced human-machine integration. Cryogenic preservation and revival research. Cryogenic preservation is progressing from basic cell storage to freezing and reviving whole organs. Using vitrification, ice crystal damage is prevented, allowing long-term storage of kidneys, livers, and other transplantable organs. In 2025, scientists successfully rewarmed cryopreserved rat kidneys and restored full function after transplantation. Future possibilities include whole-body preservation, with potential uses in extended space travel and life extension research. While reviving humans remains speculative and far from achievable, advancements in organ preservation are already revolutionizing transplant logistics. These breakthroughs could one day enable indefinite biological storage and even the revival of complex organisms when technology allows. Large-scale LEO satellite internet, large-scale low Earth orbit, LEO satellite internet projects, such as SpaceX's Starlink and Amazon's Project Kuiper, are deploying thousands of satellites to provide global high-speed connectivity. By mid-2025, Starlink had over 6,000 satellites serving more than 75 countries. These networks aim to bring internet access to remote areas, ships, and aircraft without relying on ground infrastructure, while also enhancing Earth observation, disaster response, and defense capabilities. Challenges include managing orbital debris, space traffic, and geopolitical control over communications. By 2026, both coverage and capacity are expected to grow significantly, transforming global internet accessibility and influencing civilian as well as strategic communication networks. Fully autonomous AI agents. Fully autonomous AI agents are advanced systems capable of operating without direct human control, setting their own goals, and completing tasks from start to finish. Through natural language interfaces, they can handle research, write code, trade stocks, or manage supply chains entirely independently. Unlike traditional AI, they adapt in real time to changing conditions. Early prototypes like AutoGPT and Devon have shown limited autonomy, while enterprise-ready models are being tested for 2026. However, concerns remain over transparency, security risks, and unintended decision-making. As these agents grow more capable, robust oversight will be essential to ensure safe and controlled deployment in real-world applications. Programmable matter and shape-shifting devices. Programmable matter refers to materials that can alter their shape, texture, or function on demand. Early prototypes use microactuators, magnetic fields, or responsive polymers to change form within seconds. Such technology could allow a single device to transform from a flat sheet into tools, drones, or structural components without conventional manufacturing. In robotics, this enables machines to adapt physically to different environments. Military and space uses might include gear that reconfigures in the field. While consumer-ready versions are still years away, advances in soft robotics and reconfigurable materials suggest a future where physical objects are as editable as digital files. Converting air humidity to electricity. Scientists have developed thin, flexible membranes capable of generating electricity from moisture in the air. Made with protein nanowires from Geobacter sulfur-reducens, these films can continuously produce low-voltage power without batteries or sunlight. Early prototypes have powered ultra-low energy devices, and research suggests they could scale for use in wearables, sensors, and remote systems. The material is compostable and contains no moving parts, making it ideal for powering electronics anywhere humid air exists. While still in development, this innovation marks a major step toward fully distributed, renewable energy, harvesting power directly from the environment without the need for traditional grids, storage, or fossil fuels. Self-growing, engineered living. Therapeutics. Self-growing, engineered living therapeutics use specially designed cells or microbes that operate inside the body to detect and treat disease in real time. For instance, engineered gut bacteria can sense inflammation and release targeted anti-inflammatory compounds. Ongoing trials are exploring applications for conditions like diabetes, cancer, and metabolic disorders. Unlike conventional drugs, these living systems can persist, adapt, and even replace failing biological functions. Researchers are also creating programmable cell therapies that can be updated much like software. While early results are promising, long-term safety, immune response, and control measures must be addressed before these advanced treatments reach widespread clinical use. Organoid intelligence. Organoid intelligence involves using lab-grown clusters of human or animal brain cells, often called mini-brains, to process information. Unlike silicon chips, these living neural networks can learn and adapt with remarkable biological efficiency. Researchers have already trained organoids to perform simple computer tasks and respond to external stimuli. Their biggest advantage is energy efficiency. The human brain runs on about 20 watts, far less than AI supercomputers. Potential uses include ultra-efficient machine learning systems and hybrid biological digital processors. However, the field raises ethical questions about consciousness in lab-grown tissue. Current efforts focus on scaling neural capacity and refining training without breaching ethical or legal limits. Quantum AI. Quantum AI combines the massive processing capabilities of quantum computing with the adaptability of machine learning. Quantum processors can evaluate countless possibilities at once, making them ideal for optimization, drug discovery, and complex modeling tasks. In 2025, companies like IBM, Google, and Quantinuum achieved significant progress in error correction, a key step towards stable quantum operations. Though still largely experimental, quantum-enhanced AI could eventually surpass classical AI in fields such as chemistry, logistics, and cryptography. However, its power poses cybersecurity risks, as mature quantum systems could break current encryption. To counter this, governments and companies are developing quantum-safe cryptography in advance. Mapping the universe in real time. In June 2025, Chile's Vera C. Rubin Observatory captured its first ultra-deep images using the world's largest 3.2 gigapixel digital camera, identifying over 2,100 previously unknown asteroids in just 10 hours. Beginning in late 2025, it will scan the southern sky every few nights for 10 years, tracking supernovas, asteroid paths, and potential Earth impact threats. Scientists anticipate detecting about 20 billion galaxies and over 100,000 near-Earth objects. By creating a continuous time-lapse movie of the cosmos, the observatory will revolutionize planetary defense, advance astronomy, and deepen our understanding of dark matter and dark energy with unprecedented accuracy and detail. Real-time, AI-driven natural disaster prediction. AI-powered disaster prediction systems now merge satellite imagery, remote sensing, and weather data to forecast natural hazards with greater accuracy and lead time. Platforms such as Google's Flood Hub and IBM's AI weather models can predict floods, storms, and heat waves days or even weeks ahead. New global initiatives aim to integrate seismic data for early earthquake and tsunami warnings. In 2025, AI successfully issued multi-day cyclone alerts in the Indian Ocean and forecasted wildfire spread in California. The next challenge is expanding these tools to regions with limited infrastructure, boosting response times, and potentially saving thousands of lives worldwide through timely action. Extreme environment robotics and fast learning machines. Robots are now being developed to learn complex tasks in minutes instead of months, thanks to advanced reinforcement learning. This allows them to adapt rapidly to new environments. Models like Figure 02 and Agility Robotics Digit are entering industrial trials, while others are tested in extreme conditions such as deep sea, high radiation, and space environments. These machines excel in places unsafe for humans, reducing the need for costly retraining and downtime. In 2025, prototypes successfully learned assembly tasks overnight and navigated hazardous terrain autonomously. As technology advances, these robots could take on disaster recovery, exploration, and defense missions without risking human lives. The future is arriving faster than we think, bringing breakthroughs that could save us or change life forever. The question is, are we ready for what's coming?